Okay, Jim, I think we're ready. Go ahead. You can start.
Okay, let's get started. Today so can you hear me and can see the slides?
Yeah.
Okay. Today I'm gonna introduce a, a conference paper from NIPS 2012 called Multi-Resolution Gaussian Processes. And the outline is very simple: motivation, method, and results. For the motivation part, because Gaussian process usually assume smoothness properties of the underlying functions, so the abrupt changes can be always ignored. And in realistic world, there are many kinds of data
Jim,
that.
you might take like 2 minutes to give a quick introduction about Gaussian process.
Okay.
Yeah, I want Nancy, I want Sina and Madison to have an idea about Gaussian process. A very
Okay.
quick introduction. Yeah.
Basically, Gaussian process just assume for the data, usually you have some inputs, which is denoted as x1 to xn, and n is the number of observations, and accordingly you have some scalar output. Usually it's a scalar, y1 from y1 to yn, and for data to model this data, usually we assume y is some noisy observations of function f, and epsilon here is usually a Gaussian noise in our modeling, and we assume f x1 from xs1 to fxn altogether follow normal distribution, which is usually maybe let me put this in this way. This is a multivariate normal distribution, follow a multivariate normal distribution. Usually you have a mean function, but which is mu x. X here is just all the input function, all the input vectors, and also you have some kernel functions. Usually the mean function is set to 0, and the kernel function are just some commonly used kernel functions like RBF, which is your the RBF is just a squared exponential function, decay function. This the covariance function measure and the output function are like modeled according to the relative correlations between the input vectors. I don't know if this is clear for you, Nancy. And accordingly, we can use conditional normal distribution to do predictions. And usually the model parameters are influenced using maximum likelihood estimation or some other posterior inference algorithm, like variational inference and expectation propagation.
Yeah, Jun, you should give some high-level idea about Gaussian process. So Gaussian process essentially is a prior over functions. So you can view like a Gaussian process prior will sample a particular function curve. Yeah, that sounds weird, but if you know the basic concept about stochastic process, it is just what is stochastic process is defined.
Yeah.
And then Gaussian process has a property that for any finite projection, namely the Gaussian process sample evaluated at any finite points to follow multivariate Gaussian distribution, and the covariance matrix is determined by the covariance function. So when we do the computation, you always deal with a covariance matrix, kernel matrix, and this multivariate Gaussian distribution. Okay, yeah, continue.
Yeah, so starting from the covariance functions, usually it's some, like, for example, RBF functions or other commonly used kernel functions. They can guarantee the smoothness of the approximate results. So like for in these motivating applications, like it's called magnetoencephalography recordings of brain activity in response to some word stimulus. This kind of signals are collected from sensors. Usually, maybe in some movies we can see you just wear a helmet, and there are many sensors on the helmet, and brain activities like the electronic signals are collected by using those kinds of sensors. And usually the signals have a lot of in this figure you can see there are many abrupt changes or peaks occur in this kind of signals. And this kind of signals is just basically this kind of data are time series data. And by using traditional or standard Gaussian process with smooth, or we can say it's a stationary covariance function, we already got some results like this. It's very smooth, and we can model signals with abrupt changes. So motivated by this, they want here what is stationary covariance matrix? We can simply put like see its covariance matrix, covariance function x1, x2. If the result is only related to the relative distance between these two like inputs, like the RBF function, they are only related to the result is just some functions of their Euclidean distance. So this kind of current functions is called a stationary function, which is only related to their relative distance.
I have a high level question before we continue. So
Okay.
in this data, like those abrupt changes are like normally when we see such a data set, we treat those change as noise and noisy, then we tend to stabilize the curve. Like we want the curve to be somehow smoothie. Here they believe we should also model those the noisy changes or as well.
Yeah, because uh, uh, in these applications, when you see a word, you your like neural systems can have some complicated uh, reactions to this word. So the electricity signal can have abrupt changes, like some uh, yeah to the word stimulus. It's reasonable that this kind of abrupt changes are not noisy.
And they use GP to do like a prediction or what?
Oh, there is another background information here because all the signals are collected from outside your skull. So the 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 signals can be really noisy. It means the signal to noise ratio is very low. So we can only get some reliable data by processing multiple trials of noisy data. So here they just collect multiple trials of the same might be of the same word stimulus. After some processing, they can get some underlying results of how your brain works.
Okay, so the three lines are three measures, like or three samples, and each sample is actually a noisy line.
Yeah.
Okay.
Here you can call it a trial.
A trial.
Yeah, in each trial there are many other samples.
And they want to infer the underlying two curve or line that correspond to this word or this stimulus.
Yeah.
Okay.
All you can see, they want to extract some shared mechanism of your brain, which can be reflected by a processed curve.
But this is test on the same subject. I mean, same person, right? The three curves.
Yes, they didn't mention how many people they tested, but they did mention how many data they have been collected.
So they will in their data set they will have several words and several groups of lines, and they are trying to use the same GP kernel, the learned GP kernel, to like infer different underground line. Is that the idea?
Maybe maybe they want for further word stimulus, they may first try to like split them into different categories, like buildings, animals. For each kind of word stimulus, they want to know how the brain reacts to them. Like for the maybe for buildings, like or different animals, they can have a different reaction to the word stimulus, like the reaction time. Maybe for the building, the reaction time might be faster or something like that.
Then are they trying to predict something like given your a unknown words, then try to predict uh the correspondence curve or
Yeah, their experimental setting is very tricky. First, they might give you some training trials, like 15 training trials, and then you have 5 remaining testing trials. For the testing trials, you can like predict the whole trial, or predicting or further split the testing trial into 2 parts, the training part and the testing part. And conditioning on the training part, you can get a approximate result for the testing part.
Are those trials from the same word?
I think so.
So their input is only time.
Yes. So
Input is only time.
yeah, they only deal with the time series data.
And you have a bunch of people who say the same word and record their brain activity strengths.
Yeah.
Yeah, that sounds a little weird to me, because it looks like for the same set of input, you're gonna have a multiple outputs. Right? Each output comes from one person or one subject.
Yes. Because even in the same person, you can have really complicated reactions in your brain. So we can get multiple different trials that's reasonable. But the underlying like the really the most related activities might be extracted from these like multiple trials, because there are many other activities in your brain, not only this reaction, this kind of reaction to the word.
So like I'm not very sure about the like brain science. So are they assume that there will be one correct response, or they're trying to generate a series of response? So if given a word like a car or animal, could we expect there's a true curve that corresponds to this word, but we don't know the true curve, or they just assume that given a word there will be a distribution of those curves, and they just want to sample some curve with high probability.
Yeah, you can also treat these trials as multiple like simulations of distribution. Here it's just described by the Gaussian process.
Yeah, let's continue and say what's the notation, and then we get a better idea.
Yeah.
Okay. According to their paper, their contributions are these 4 points. First is direct interpretability. This contribution is application related, and I will explain this in the result part. And the local stationarity it's based on how they construct their non-stationary kernel, and the irregular grades of observations for the time series data, usually for in other standard algorithm to predict or analyze time series data, you you might always need to get a regular grade of the time. That means the time points are evenly distributed. Here, it doesn't need that requirement. And here it can, in this model, it can share the information across related time series. Here, it's just share the information across the multiple trials, related trials. And here is how they build their model. For the data, we this here, the notation here is only for one trial. And it's a standard notation, like the output data y1 from y1 to yn, and x1 to xn, and the observation is some noisy observations. And
So why the input dimension is p? So if it is just a time series, the input is just a scalar time, scalar.
They just list a more general notation here, but their experiments only they only do experiments with the time series data.
So p is simply 1, right?
Yeah. And they are trying to build a hierarchical structure by splitting the input domain. Here, the superscript indexed the number of the layer. Massive code A0 is just the whole input domain, and for each level, all the partitions are mutually excluded. Means AIL intersect AJL equals to empty set, and the union of all the partitions, just the whole input domain. And the subscript here index the partition in each level. On the right side, this figure gives the illustration of how the time domain can be partitioned.
So it's a binary partition, like a binary tree.
Yeah, it's a binary partition.
So
this one is A0, and this one is A1, and this one is A2. For in each level, you can further have a index to index the partition, and between levels, each partition is further binary partitioned by some point in those partitions.
So they want to construct GPs for each partition at each level, right? So
Yeah.
basically, if you have two partitions, like the first figure, then we need to construct two GPs, and for the second, we need to construct 4 GPs and 8 GPs accordingly.
Yeah, they are trying to build some dependent Gaussian process between levels, but in the same level, the Gaussian processes are independent. to each other.
Yes, so graphically, it will look like a binary tree where the leaves are the finest GPs, and the root is the target GP. But we need to, at each level, we need to condition on its the children GPs and aggregate that information to the root, level by level to the root.
Each level here is the how they construct.
Right.
Here this one is the parent node.
Mm-hmm. Okay.
And this one is the child.
Oh, it's like downwards.
Child node. Yeah, child node.
Downwards passing. Okay. Okay. All right.
The CIL is the covariance.
Yeah,
function.
here is a covariance function.
Is this a partition? I mean, of equal size, or my recollection is that they have some to determine.
Yeah, this is a very good question. They assume the partition is given, but there is a section of their paper to describe how to infer the partition in a probabilistic way. They just use MCMC. Here they use the independent chain Metropolis Hastings sampling method to sample the partition.
What's the notation like FL, AIL? It's or what does it mean?
Take AL for example, the superscript index the level of your partition, and I means here I index the partitions in each level. Like here in the level 1, you can have 2 partitions, so it's A11 and A12. In the next level, you can have 4 partitions. Like I can range from 1 to 4.
Okay, so this so the mean is given by its parent applied to this H point.
Yeah. The mean is given by the parent process.
Then how many GP are in the final layer?
Actually, by integrate out the intermediate levels here, you can have a marginal Gaussian process, and the kernel functions can describe in this way.
Okay.
Actually, you can treat this, although they describe how they construct the hierarchical structure, you can treat it as a way to construct the kernel function. Not the GPA itself. You can simply just treat all the procedures are procedures to construct a complex kernel function.
Is there any justification why the child is conditioned on the parents? Because to me, I think that the parent, it's more reasonable that the parents is depending on the child, because if the partition is more finer, it means that we need to capture more local information. Then we transfer that to global. I think that's more reasonable.
Because they want to capture the long range effects between different inputs. So they model the long range effect using the parental node, and for the leaf node or the children node, they do some like different operation to make it different from other partitions.
Okay.
From
yeah,
other,
yeah,
yeah.
cool. Yeah, I understand. Thank you.
Yeah,
You can
so
treat parent nodes as some like shared information.
Okay, yeah, I think so.
Okay, so it's like the top functions like apply to A0. It could be more stick, like it change more smoothly. Then down the way, the function, the kernel could be more flexible than to capture their local changes.
Yes.
Uh,
uh, hi, hello.
Oh.
Oh, can you hear me?
Yes.
Oh, okay, good. So, my question is that so it looks like that the A1 and A2, the parent and the child, has some redundant information. So why it's better? So why not just for A2? It just have the for A2, it just describe the fan feature of the signal. So why the redundancy is better here? I assume it's better.
Because actually the difference between, you should know here, the covariance function is different. So in different resolutions, we can have different correlations. So it's not totally redundant, but it's just it can reflect different like correlations in different levels. So in lower level, you can have more like more drastically changed covariance, but in the upper level, you may have more smooth changes.
Something like that, Xin. So,
Yeah.
so this mean function, if you Gaussian process mean function, you can view it as a function like some function, some already known function plus an additional function. So this is the parent, and this is the children. So if you want to get a final level of estimation of function, well, in the more upper level, we want to capture the general trend of that function. That is the low resolution estimation from parent node. But then you add some abrupt perturbations locally through this local covariance matrix, and you add them together, you get your final curve, like something like that.
Yeah, I see your point. So why for A2 just to describe the fan signal? I mean, we can add them up together finally.
This is just the assumption.
Okay.
I mean, if you want to model a complicated function, you always have to assume some structure. Like what you have observed, the brain signal examples shown by Jun, you can see them something like that, right? You have some jitters at some places, something like that, right? So well,
yeah,
naturally you can assume, okay, this function actually can be considered as superposition of two curves, right? One curve is a like smooth one. Like you can okay, this guy, those perturbations are just smooth out. This is one curve. You can view like it's a kind of low resolution estimation of this whole function. And then on those local regions, like in this region and in this region, you want to add some another Gaussian process to capture those local perturbations. So when you add them together, you superpose them together, you end up with more complicated curves, but at the same time, you capture the global trend.
Okay, I see. Thank you.
Yeah, this is the idea. We actually have done quite a few like multi-fidelity Gaussian processes, multi-fidelity modeling. So this can be viewed like a very early work of multi-wire solution Gaussian process. Is definitely for us worth looking at it again.
And another question is, so it says that they will assume the partition is fixed, right? The partition over the domain is fixed.
For now, they assume the partition is given, but afterwards they'll give some like algorithm to tell us how to infer the partition.
And I mean, yeah, I mean to say they assume the curve will behave basically the same in different domain, right? Could I? So if one curve like there's a looks like this, and another curve looks like this, it will fail. So supposed to be partitioned into these two parts, and in the first level, the function should work fine, or capture the overall training, but the second level, the changes here will be very fast, and here will be very slow, like A11 and A12. They will have some conflict kernel here or non-compatible kernel.
The kernel for A11, A12 can be different.
Yeah, I mean, I assume they consider this the different trial should behave basically the same in the same partition. Then right. They expect the second line to also look like this.
Oh, okay, I got a point. They have to make such assumption. If you assume like in the first partition they have like perturbation like that way, a second trial should perturbate in a similar fashion rather than have a drastic pattern change.
Actually, if you want to get a perfect fit to the data, you can like further partition A1 into smaller parts, and you may get some like better fitted kernel.
Okay. So anyway, it's the partition dependent in their setting.
Yes.
Okay.
And here they also give some intuitions about how to set the kernel parameters here. So they just use the x squared exponential kernel here. They gave the magnitude of the kernel function d and the length scale of the kernel function kappa here. They said the in the same level the magnitude of the kernel is the same, and the length scale is defined in this way, and they also restrict the sequence of the magnitudes of each level in this way, and it can make sure that it varies less from the parent function. They still want to make the children functions more similar to the parent function. And these parameters are hyperparameters. They are fixed. They are not learnable, because in the following slide, you can see that they can have a analytical like form of their posterior distribution.
So they manually select kappa and the DL.
Yeah,
And kappa, the kappa for different impression is like determined totally by their what was that, the L2 norm over?
yeah, these parameters just serve as the
length of,
hyperparameters of the prior. So the posterior, you can get your posterior distribution from the data.
okay, so that mean if the length of the partition is shorter, then the length scale should also be less.
Yes,
and directly
they
determine.
just want to make it consistent with their parent functions.
Okay.
They don't do ablation experiments about this, how parameter settings influence their experimental results. So I don't know if this is the best choice. And by integrating out the intermediate layers, we can get a marginal Gaussian process in this way. And the final kernel function, covariance function is this one. And we can see it's obviously it's a non-stationary kernel because it is determined both by the relative distance and the input locations. Because we have to calculate this kernel, we have to know the location where the which partition our input is in.
Is G the function at the finest level?
So, sorry, what?
G, I mean G here.
You mean which G?
I mean this G.
Oh yeah, this one is
It's a function value at level big L.
Yeah, here is the definition of G. It's the noise-free observation of and the G is the final level of the leaf level of the hierarchical Gaussian process.
Yeah, let me look at the how they do the integration. So A is the partition, right?
Yeah, A is the partition. Here the partition is given.
Partition is given. So P of F0. Okay. And G here should be the function value at all the training points, right?
Yes.
Oh, so KLIG are only kernel matrices at that partition. Okay. So why do you say it's non-stationary?
Because it both depends. Given two, if we want. Oh, sorry. If we want to give if we want to give the covariance between x1 and x2, we must know the location of these two inputs, because if they are not in the same partition, their covariance is 0, right? If they are in the same partition, then their covariance will be calculated according to their relative distance. So
Okay,
the-
okay.
so you must the location information and the relative distance must are both required to calculate this kernel function.
It's actually partition dependent.
Yeah,
Like if x1 and x2 is here, then the covariance is just one kernel. For example, this is the very first level. But if x2 is here, then it is kind of addition of several covariance functions.
yes, yeah. If you calculate it recursively, you can get more clear idea of how this kernel works. Like if you have two, all these are the inputs, and here is x1 and here is x2. So in different level, we can have different partitions.
Yeah, you have to look at. Well, I guess we would just look at the biggest partition where it contains both x1 and x2 and then go back toward the root node, right?
Yeah,
And you just calculate the covariance function along that path.
yeah. Or in other way, you may need to find all the partitions that include both points and
Yeah,
calculate.
that's what I'm saying.
Yeah.
Yeah, that's what I'm saying. You just what I'm saying. You just look at the biggest the smallest partition which contains both x1 and x2, and you just look upward until you reach the root node, and along this path, you're gonna add up the covariance along that path.
Yes.
Okay. Okay. Yeah, that makes sense. That's yeah, that's really interesting, actually.
So
It's
So
very
they
simple
also-
to construct non-stationary kernel.
yeah. They also said it's both continuous and discrete. Continuity is reflected from the local covariance function that use their relative distance to calculate the covariance, and the discretization is reflected from the discrete partition. And here, because so in this slide they further come back to the applications, the brain activity applications. They want to find the root node function.
One more thing, Jim, before we get to the computation part. So if you consider in a stochastic process point of view, like they only calculate, they have an effective covariance only in that partition, right? For this partition specific function. Like if you are in this partition, you have a special covariance function, say Li, right?
Yes.
Inner full covariance is here. Yeah.
Oh, just
Either-
a second. The connection is very slow. Sorry. I may need to stop the share and reshare it again. Okay.
Yeah, we can look at this slide. So if you look at here, when xi, xj are outside of that partition, their covariance is simply 0.
Yes.
So that means, I mean, if we just construct Gaussian process with CRL, they're essentially another curve, right? But here, when you specifically define your covariance function, only have non-zero at this partition, and outside the partition simply zero. Isn't it like a truncated curve?
In other way, you can
Something like that.
yes, you can also think it in this way, like you can just split your original curve into different groups and modeling different groups by different Gaussian processes.
Yeah, but outside of the group, you just make the curve value to be zero.
Yes, and the final results are calculated in a additive way, additive way. Yeah.
Yeah, but it isn't like just like wavelet.
Yeah, it's like truncated kernel. Then you need to the partition effectively is define the range of this truncated kernel.
Yeah, it's truncated. I would rather say it's truncated curve, but in whatever way, like you have some curve which is only vivid at some particular region, like particular partition, and outside this partition, you're simply set to be zero.
Yes.
And then isn't it just like wavelet? Right? Wavelet is just to use some kind of local wave to capture the local properties of the curve.
Yes, you can even do it in a more crazy way, like several segments of the curve is in the same curve you just draw. Like one, two, three segments, three discontinuous segments is in the same Gaussian process.
Yeah, like you have a rough Gaussian process, like a rough global curve, but at each partition you might have something like that, something like that, something like that. But for each segment, I mean, if you will the whole input domain, they're just a truncated curve.
Yes.
And you just add them together.
Yes. Or even discontinuous points, not even a segment.
But here, this is not discontinuous point. This ARL is a one segment, right? This is in the time domain.
Yes. I mean, you can do that in using some other methods.
Yeah. Let's continue.
So I have a last question about the model. So generalization seems only work on one dimensional. If it's on multi-dimensional, how do they do the partition? It will be exponentially. It will increase exponentially. Right? The number of partition.
Yeah, they did mention it in their paper. They said that you can do like the space partition using Voronoi tessellation. It's just I'll give a simple example here. Like you have this point, like partition point here, and using the perpendicular bisector, and you can partition the space. Here is the 2D dimensional space into like partition the space in this way, and then use some tree or graph algorithm to do the to group them into different levels. Like this adjacent partition can be grouped together, and these two can be grouped together, and these two can be grouped together, and these two can be grouped together. Sorry, no overlapped space. Maybe we can first group this four partitions firstly, and then in the upper layer. we can further group this into
Oh,
into the
okay.
whole domain. Yeah, okay.
It's like hierarchical clustering.
Yeah,
Um,
you might need to use some other graph algorithm. It might be expensive, so they didn't do the real experiments in their paper.
Okay.
And they came back to their Mac, the brain activity applications. Here they want to find the underlying all the root node function patterns by using the observations and partitions. Here it's just a conditional normal distribution here, and they also give the predict distribution. These are all analytical given the partition.
What's F0?
Third one,
What is F0x?
which one?
Just the root. What's the root?
Yeah, the root here is the most smooth one. Here it should be this one. Here should be the the F0 is not a Gaussian process here. It's just some function. But the conjugacy gives the form of normal distribution. Gives the form of F0, and it's also a normal distribution here. F1 means the F1 means the function value of the first level, and F2 means the second level. F0 is just the corresponds to the partition A0.
And okay, what is Y1 to Yj? Is J data point or J
Oh
child?
yeah, here these are multiple 12. Here all the formulation above is only for one 12. And by aggregating these formulations together, we can get a formulation of F0 conditioning on multiple 12. Here a 12 is just one curve. Here, given multiple curves, you can get a I see here is a root function here.
Okay, so the X for the different child will be the same.
Yeah, they are the same.
So they assume that, okay, you're gonna use Gaussian process to sample one function curve. And then given this function curve, you measure it for J times, you got J trials.
Yeah.
Okay.
And then here is a marginal likelihood. You can, I don't know, maybe this can be some, because the kernel parameters are given, so it doesn't need to be learned. So this might just some measurement of the model performance.
Yeah, model evidence. Yeah.
And for
Oh, this is a model evidence for a partition, right?
yeah,
Different partition will give you different model evidence. You can maximize this to find the partition.
yes, but in And here they just gave the how we inference the partition by using our observations. So they just like first gave a definition of normalized cut. So it's just oh, sorry, yes, I didn't list the how to calculate the cut of A and B. A and B are just some subsets of the partition you want to further partition. Like here, it can be this part can be A, this part can be B, and you try different combinations and find the different combinations of A and B. You can have different normalized cut, and according to the normalized cut, we just gave a proposed distribution. Here, proposed distribution is a concept in Monte Carlo, the Markov chain Monte Carlo sampling method. So they just use the importance sampling. They both use importance sampling and independent chain metropolis Hastings sampling method to sample the possible partition, and use those.
What does
samples
associate AV mean?
V is I think it's the whole set of the observation points. These are all the input domain points.
And A and B are two sets, right?
Yeah.
And A union of B is the V.
Actually, it should be A union B equals to V, and A intersect B equals to empty set.
So how do you compute the cut?
Sorry, just a second. Let me see there.
Yeah, I think it's a term from graph theory.
Yeah. Just a second. Oh, here cards us equals to yeah. And the W here should be some weight. Maybe here they use the importance sampling to calculate the weight.
Importance sampling. I think W is some pre-assigned weights, right?
Yeah, but they didn't mention how they calculate it. Oh, here it's the it's the element of cost function W. Cost matrix W. Here, the matrix W is just some empirical correlations calculated from the multiple trials on different locations.
Oh, so if you have n points in this trajectory, your W is n by n. It's adjacent. You can view it as a adjacent matrix.
Yeah, correlation matrix. They didn't give how they calculate this cost matrix in detail. and I can't
It
find their
says,
code.
it says
either.
imperial correlation matrix. They just calculate the imperial covariance matrix
Yes,
because you have multiple trials, right?
yes,
So each element, which is the edge weight, you can view as a fully connected graph,
yes.
and they have their weights computed as their correlation, and they just want to maximize the card or minimize the card. I can't. They should maximize the card.
So the card is just some reference to for you to calculate the proposal distribution here. The inverse of the normalized card is proportion to the proposal distribution.
Proposal distribution.
Yes, because you need to use Metropolis Hastings sampling method here. You must have some proposal distribution to draw samples.
Okay, but their prior about partition is what is uninformative.
Is uniform distributed.
Okay.
And here is the pseudo code for the partition algorithm. They further define a global search algorithm and a local search algorithm. The idea is similar. You just pick one partition node and do the partition, draw some samples from the proposal distribution and calculate the acceptance rate. If it is accepted, you just replace it with replace the old partition with the new partition and update the corresponding kernel variance.
But
Here,
they have the pre-specified L, right? The levels, number of levels.
yeah, the level is some given value for
Okay.
an experiment. The only important line here is just this line.
Okay.
All the other lines are just for the kernel update.
Yeah, that's pretty standard. So what this is called global search, right?
Yeah, global search is because the selected node is the root node, and so it's global search. If the selected node is some intermediate node or leaf node, but yeah, it's just a local search.
What does it mean by leaf node?
You have a partition tree here. If you select the root node, all the nodes should be repartitioned again. And if you just select an intermediate node or a leaf node, you just need to repartition the leaf node and its corresponding descendants.
But how do you know other nodes? I mean, you need to use a proposal distribution to generate the partitions, the whole partitions, right?
Yeah.
Or in other words, to generate the tree. In the global search, I can see that you're gonna start from the level one. Actually, start from a root node. Root node is the whole set. You don't need any partition. But then you're gonna from level 1 to level L-1 to get all the subsequent partitions or nodes.
Yes.
But for local search, how do you get those tree nodes? The partition with each tree node.
Yeah, they just like for you already know the global partition here, so you just select one according to the L star and V star, you just extract the selected node and find which partition is in the selected partition and extract those index as well, and then do the repartition in the same way as the global search.
But in that way, you just okay, they select the tree node to repartition. But A,
Yeah.
L star, V, new star, what is that? It's node proposal.
Yeah, because we have the proposal distribution, you have to resample the partition again from the node partition.
But
From
you,
the
you
node
know which
proposal.
node. You need to which node. Well, I mean the previous like normalized cut, it just tells you given V, well, what is the proposal of the partition of this A, like A and B, right?
Yeah.
So what does it mean? It just means that I'm gonna associate A with some intermediate node in this tree.
Yes, because given this observation points here, you can have, for each partition, you can have a normalized cost, right? According to this cost, we can have we can model how the partition is distributed, and that's the proposal distribution. And each time for the local search, we just randomly, I don't know how they pick the L star and V star. They don't give the details in their paper, but we just randomly pick some node. Here is just randomly pick some level and some partition in that level, and we just repartition that node and its corresponding descendant node.
Yeah, that sounds a little weird because if you choose the intermediate node, right, you can use this normalized cut proposal to get the partition for this particular node. But for example, it is A, and for the remaining part is B, right? B will cover all the other partitions.
Yeah.
Then you have to.
Yeah,
well,
they did
still adopt to some procedure to do that. Sounds a little.
Yeah. Yeah, I'm not very clear about this part either, because the paragraph in the paper is very limited, and the pseudocode is also very big to understand. And I can't find their code. They didn't publish their code in the GitHub.
Okay, that's fine. That's fine.
Okay.
Yeah, but most reasonable way I think is the global search. That's very reasonable. You can view their for loop is just a sampling of the partitions, a sampling of this tree nodes.
Yes. And for the experiments, they just did two. Yeah, basically it just did two experiments. One is on synthesized data, which is generated by its own model, a 5-level multi-resolution Gaussian process. For they just generate like 100 trials here, and each trial is 200 points. And for the real data, they just use the brain activity data, and they tested on 10 words. And the helmet they use have 102 sensors. And for each, I mean the experiment, they just use 15 training trials and 5 testing trials. Each trial is of length 340. And here I will also introduce their competing methods, hierarchical Gaussian process and wavelet-based functional mixed model here. Hierarchical Gaussian process here is it's not a standard hierarchical GP. They before they got into the Gaussian process, they first model their data in a latent model. In this way, the observation is it's like low rank approximation, and they further like put some Gaussian process prior over eta here, and eta is further a noisy observation of some functions here, and this function is formulated in a 2-level hierarchical Gaussian process prior way.
What does tau mean?
Tau means which one? Tau here, I think it's the input.
It's time.
T is the time. Tau might be the input.
But here the data is just the time series, right?
Yeah. Tau here. Oh, just a second. Here I just want to give a rough idea of how the hierarchical Gaussian process is proposed. So I didn't go to the
Yeah, that's fine.
into the
I'm more
details of
interested in a wavelet functional estimate. They
yeah.
also compare with wavelet.
And it's still the final. You can also integrate out the lower level of not the lower level, this level of Gaussian process out and get a marginal Gaussian process, and you can see that the kernel function is still a stationary kernel. So the local characteristics might not be reflected in their model. And for the wavelet-based functional mixed model, and here I'll give a brief introduction of wavelet transform. Actually, if you know the Fourier transform, we can transit from the Fourier transform to the wavelet transform by recognizing that they are both methods trying to formulate a given function in some other space using the orthonormal. Yeah, I think the term should be orthonormal basis, which is what is orthonormal? That is each basis is orthogonal to each other, and their norm is just 1. So they are unit basis, and they are orthogonal to each other. And a frequency part in the Fourier transform, you can also treat it as the index of the basis. The index in Fourier transform, the index is just the base term in the sine and cosine function. And in wavelet transform, the index has 2 indexes, which is they call a dilation term and the translation term. here, here this one is the basis. Here, this one is a basis, which is indexed by the G and key here, and this function here is called the mother wavelet. In Fourier transform, is you can like make by comparison with the Fourier transform, you can it's just a sine function or cosine function, but in wavelet transform, it's just some truncated function, like this. It does not expand over the whole real domain. It's just some truncated function over a small part of the axis. And how the I didn't list the so it should be sorry, just a second. Let me find okay, given a function fx, we want to use some basis function to represent it, like in Fourier transform, we just approximate the function this form is a wavelet transform, and the frequency part is indexed by two numbers, integer numbers, J and K, and this is a form of Fourier transform. The frequency part is indexed by just a integer value. So I just want to make it easier to understand. They are just both transforms are just using some I call it also normal basis. And in the Fourier transform, it's just sine function and cosine function. And here is some in wavelet transform, it's some predefined functions by doing the translation and dilation. And in wavelet transform, the coefficient is calculated by using this kind of integration here. And similar to the discrete Fourier transform, we can also have discrete wavelet transform by discretizing the frequency domain and the time domain. And here is some example of the mother wavelet, just this function here. And as you can see, by multiplying with this term here, we're just doing some dilation by expanding oh, sorry, it's not this term. It should be this term, not doing the dilation. We just expand the mother wavelet or squeeze the mother wavelet along the time domain. And for large delta t, the delta t here means the weight of the mother wavelet. If it's large, it means low frequency and large scaling factors. The scaling factors should be the 2 to the power of g. And if delta t is small and we got high frequency information, and it also means smaller scaling factors. So
Jay, that
and
should
here,
B, right? B is a shift. B is a shift. B just indicates the location. The
yes,
size A indicates the granularity.
yes, or the yes.
So
And
from just to give you like all kinds of A and all kinds of B, you want to decompose it as a mixture of these wavelets.
yes, and given a mother wavelet, you can like expand or squeeze the mother wavelet and put it in different locations and do the convolution operations with the original signals. You can get like frequency information about you can get information of different frequencies and of different frequency information about signals in different locations in the time domain.
That's the
here
B actually indicates the locality.
location.
Yeah.
B indicates the indicates the location in the time domain.
And A actually indicates the resolution.
Yeah.
So this is a natural way of performing multi-resolution, right? Multi-resolution
Yes.
learning.
And here is a comparison we can do to better understanding the scaling factor and the shift factor. For the Fourier transform, we just use sine or cosine basis to decompose the signals, and we only have the frequencies information of the signal. We don't know the location in the time domain. We only have the frequency information of the signal in the whole time domain. And time frequency analysis is just to split the original signal along the time domain into different parts. And for each part, we just do like a Fourier transform and get the frequency information for that part. So we both have time and location information and frequency information, but it highly depends on how the result highly depends on how you partition the time domain. And wavelet transform sort of provides a more natural way to do the time frequency analysis. And by manipulating the scaling factor and the shifting factor, we can get a continuous, because here, although the G and K is integer valued numbers, but after doing the binary dilation and the binary shifting, we can get a more continuous and a more natural way to do the scaling and shifting. And the ABC here is some examples of mother wavelets. So
There is
automatic.
there's a discrete version of wavelet transform, like
Yeah.
PFT. So I have like discrete algorithm to get wavelet transform.
Yeah, the transformation. In fact, the transformation can be conducted by using the fast Fourier transformation. Yeah.
Okay.
So it should be like mature technology to do the multi-resolution analysis. But there is one. Oh, here is how we do the discrete wavelet transform. We just discretize the here Cn should be the frequency part, and tau m should be the shifting factor. This one should be a scale factor. This one should be the shift factor, and by discretizing them, and we can get a discrete formulation of the transform.
But it looks like it's much more convenient to and much easier to just apply a wavelet transform.
Yeah. Remember that they're one of the four contributions of this paper is that they can conduct their methods on irregular grades.
Okay.
Right.
So you
So
don't
here,
have you don't have an
yeah.
even space.
Yeah, to apply a
Sampling.
standard discrete wavelets, you have to have a regular grade of data.
Okay.
And here is wavelet based functional. I think I don't remember the name. It's functional mixed model, and they just first project the observations into wavelet space and feed the data using some Bayesian methods like posterior MCMC to get posterior samples, and then project the wavelet estimates back into the original data space. And
that is called inverse transform, inverse wavelet transform.
Yeah, they have forward and the inverse transform both.
What does FMM mean? Function mixture.
FMM is functional mixed model. Yeah, because they model, this is the formulation of their model, and they model B and U in a functional way. They are the function of time.
You mean, but if you do the after you do the wavelet transform, you're actually modeling those. Okay, you are assuming those transformed coefficients are as function of frequencies, or functions what?
They should be the function because for indiscrete wavelet transform, the scaling, the J and K are fixed, and
what you get is just the coefficient of the.
Yeah, you just need to
basis.
like estimate the wavelet coefficients here, and the J and K are fixed.
So they will see JK as a function of A and B or something.
Yeah, they should be the I think it might be the time. Yeah, I didn't recall the details of this formulation here. They just it should be it should be time, because they got N12 of time series data of length t. here, as you can see here. So they just give you a regular grade of observation, and you did the transformation and calculate the coefficient in this W prime here. Actually, in the discrete wavelet transform or discrete Fourier transform, the index is just some integer values to index the order of the data.
Yeah, I'm a little confused here because for wavelet transform, looks like there's no frequency domain. You just have different choices A and B. Different A and B index a specific component, like specific basis. You just estimating the coefficient.
Yes, you can also, actually in Fourier transform, you can also treat the frequency domain as some index, because they only
that's why I'm asking you if they just will CJK as a function of A and B, like if you will A and B as frequency. Like in Fourier transform, you actually will like.
Oh yeah, it should be the function of J and K, but
then that makes sense.
But in their modeling, it might be some other functions of other inputs, because J and K are fixed. It should be the function of J and K. Yeah, correct.
J and K or A and B, whatever, but it's the same thing. Okay, yeah, let's continue. Let's look at the experimental part.
Okay. And here they gave the results of synthetic data, and A is here A and B. They want for the synthetic data. They just want to show their partition algorithm work. And for A and B, A is the true partition and the B is the MAT partition. I think the result is averaged over multiple samples. I mean the samples of partition.
How do they get MAP partition?
Maybe here they mean the best partition.
Because they use Monte Carlo sampling, right? They use MH proposals. How can they get MAP partition? Or they just on the posterior samples who gives the maximum likelihood or maximum evidence?
Yeah, because they got multiple like some posterior samples, and they just choose the best one that gives the highest likelihood.
Okay.
And for C is the plot of 10 Monte Carlo for 10 chains. Yeah, it's for some chains here. Chains here should be the Markov chains for the sampling process. And how the likelihood change during the training process. And D gives the and HGP is just stands for the hierarchical GP, and D gives the errors posterior mean of F0 and true F0 for different methods, and the multi-resolution Gaussian processes give the best results. And for the figure E, they also tested how the level the number of layers or levels of their models react to can influence the performance of their model.
Okay.
The held out means the testing performance over the five other testing trials. And here is the real data result. Here the visual frontal. This means the different part of our brain, because they have many sensors. They are located on different parts of your brain. So they, according to those regions, they just provide the result. The first A and B just MSE performance compared with Gaussian process and hierarchical Gaussian process. And C is the C is just the testing prediction for different methods. The green curve should be the average value of testing trials, and you can see here there are more methods can give a more can detect the abrupt changes. And they also gave the held out likelihood compared with the wavelet transform-based method.
But they don't show wavelets, the decrease in MSE versus wavelet WFM.
Yeah. Yes.
Okay, when it looks like when the number of data points is small, the decrease of MSE is much more significant, right, than HGP. But when you have like 300 data points, the advantage is not that significant. It's less than 5%.
Yes.
If you look at the figure B. And for Gaussian process, looks like the more data points you have, the better improvement you got from in MSE.
Yes.
These are all their results.
Yeah. And they also show some other, like explore some interesting results here. These are just some, I think, heat map for the curves in the first level, but they didn't specify what was the color in the figure mean, and they didn't give a like color axis here. So, but according to their analysis, their results coincide with some biological discoveries, like the reaction time, how different part of our brains react to the word stimulus. And here is another paper about how to construct the non-stationary kernel. They just use some methods to first group the observation points into K groups, and these K groups are first modeled by a Gaussian process, and here Z is some code to encode how the observation inputs are grouped. So according to their category, they further build a Gaussian process prior over the observations.
Oh, it's kind of
And,
similar because you still look at it, the kernel is a group related. It's
yeah,
kind of like a partition related.
yes, and actually in this paper, this is also a next paper, but there are many details that are not very clear, and I can't find their code either. So the result is I don't think they can really get that good results, because this paper outperforms other state-of-art methods largely.
Is the paper you sent to me before?
Yeah,
The NeuralNIPS 2019?
yeah,
Yeah, I know this guy. We were in the same NSF panel last year. Yeah, we can take a look at his method.
and according to this paper, maybe we can do they all do the like partition or clustering or even the classification in a deterministic way. So can we do it in a non-parametric way, like either the points are in the time order or not? We can use some non-parametric processes to do the partition first, then based on this partition and apply the Gaussian process here, and we can automatically determine the number of groups.
Okay.
And that's it. Any comments or questions?
Yeah. Any question?
And
So-
like, you go first.
Hello. Okay. So on this slide, so for the dirichlet process, why I did not get why it can do the parametric time domain partition. So could you explain it a bit?
A Dirichlet process is commonly used prior to for the. I think sorry, it's I didn't so it's commonly used prior for classification. I think I did it several years ago, but I didn't remember the details. But it's a non-parametric way to select, to determine the number of groups for maybe you have heard the Chinese restaurant process and the stick breaking process. They are all the same direct. They are all directed processes. So we can. I for now I don't have an idea how to construct the one exact specific way to determine the number of clusters, but I think there is, because Dirichlet is always a good tool to determine the number of clusters. I think we might find some way to figure it out to get a good formulation to get the number of clusters.
Yeah, okay. So you mean that if you if given the number of the clusters, so it's easier to use the Dirichlet process. So actually, I didn't understand the parametrics. What do you mean the non-parametric scale?
Non-parametric theory means the you don't have the parameter. Non-parametric doesn't mean you don't have parameters.
Okay.
But instead it means your parameters increase with your data, because Gaussian process is a like typical non-parametric method, because as your training data increases, you must for further prediction, you must use all the training data to get the approximation. So the training data, the size of the training data increases, the parameter of your data. Maybe the parameter here is not a good way to describe the parameters of Gaussian process, but the more data you get, you must use more to do the approximation. The parameter of the model is not fixed.
Okay, I see. So another question is that, so could you go back to the graph card?
Oh.
Yeah. So actually, I didn't follow why the hierarchical partition are introduced here. So this is a different method than the multi-resolution Gaussian process, or this can help to explain it. I didn't get it well.
Because in the all the formulation before this slide are
Okay.
given based on are derived based on a given partition, right?
I see.
So yeah, so here they just gave a way to formulate how the partition would be, the distribution of the partition would be imposed. So here they just here we want to draw the posterior samples of the partition. The assumed prior for the partition is a uniform partition along the timeline. So they here to draw the samples from the posterior distribution, they use some Monte Carlo Markov chain Monte Carlo sampling methods, like Metropolis Hastings sampling methods. to draw the samples. And in this kind of sampling method, they first draw some samples from the proposal distribution, and based on the likelihoods and the proposal distribution, they might come up with some acceptance rate to decide whether the sample should be accepted. And then based on the acceptance rate, we will accept this sample or reject this sample. And all the methods are developed based on the Markov chain. And usually the acceptance rate are just some transition and transition.
You don't go to that detail.
Okay.
Don't go to that. You don't need to go to that detail. Just in just one sentence. If you want to find a partition A which can maximize this model evidence, that's the goal.
Okay.
Like you can do the new combinatorial search, like what we have done for network pruning, right? That's a combinatorial search. You cannot do that. So they have many other methods. You can use greedy search, and Markov chain Monte Carlo sampling is just a stochastic search.
Okay.
Right? That's why, our method you can consider to construct Markov chain to do that. We don't have time. Yeah, we don't have time when we did the submission, but after that we can definitely think about that. So if you assume P of A is uniform, right? Markov chain Monte Carlo sampling is just to ask you what's the posterior distribution of the A, right? So in most of the cases, the mode of the posterior distribution is the maximum. Who gives the maximum of the joint probability? So Markov chain is just a way to do that.
Okay. Okay. My last question is that so for the multi-resolution Gaussian process, so did that decided A0 first, and then A1, and then A2?
What do you mean by?
I mean, did that?
You mean the partition or the?
Yes, the partition. Did that decide the partition, the parent partition first, and then decided its children partition?
It's a good question. In their paper, they did mention how they generate the partitions. They said if you generate the partition in a dependent way, just like generate the first level partition, then the second level, then the third level. That can result in an unbalanced partition tree. They didn't give a very convincing statement that how would that give an unbalanced tree, but they did it in another way, that is to jointly sample all the partition points along the time domain, and then just join the adjacent area into a node, and do the binary partition in that way. They sample all the partition points at the same time.
Yeah, I feel it makes sense to me because originally I was thinking, so if it gets a partition dependently, so what about if we have a bad parent partition, and then how will it affect its children? So yeah, so I think your explanation makes sense to me. Thank you.
So in this series of work, it seems like they focus on how to partition the input domain. So are there like other work in another direction that does not focus on partition the input domain, but the true hierarchical resolution? So they could adaptively determine in which like suppose we are dealing with time series prediction, we will be given a series of time, a series of observations, and suppose in the grid, in the regular grid way, and then they could automatically determine how many layers or how many hierarchical functions to do. Are there work like dealing with this direction?
Like the most recent one is just I think it's just this one that use like clustering method or classification method to do the group first, then do the what I mentioned in the last slide here is just it's just to I just want find a way to do the like if you only have two layers, for the second layer, can we like do the partition automatically, not just in a binary way, just do the partition automatically, find different groups. But I did think about how to automatically generate the layers, but I didn't figure out a way to do that.
Or it might be more clear, like so if we are given such a like time series, if we are given such a time series data, then we want to predict this part, maybe we could use like several layers of function here, but because the function values change drastically in this area, but if the function is like this one we are given, then maybe we don't need to use that much layers of functions. But now in the setting, we just, no matter we do, but we just participate this domain into participate the input domain into different sets. And
my initial thoughts is just for a sequence of time series data, each time we got one observation here, and we either put it in the existing categories or create a new category. For each category, we have level Gaussian process, and for all the categories, we can have upper level Gaussian processes. That's why I mentioned the Dirichlet process here, because there is a famous example of Dirichlet processes called poly-on. You just pick some ball from a bag. If it's a black one, you just create a new category, and otherwise just put it in its own category.
Mm-hmm.
In this way, we might generate groups automatically.
Okay, nice. Yeah, and that's quite a very like interesting direction, and it's worth trying.
Okay, yeah, I think we have to stop now because I got another meeting very soon. So yeah, that's very interesting talk. And why I want Jun to introduce his work, because we want to do some domain decomposition work related to PD, but it looks like this idea kind of apply to that kind of problem, but there's some difference. We can definitely think about that. And right now, like multi-resolution learning and multi-fidelity learning are kind of like attracting people's attention in many areas, especially in the physics simulation domain. Okay, thanks, Jim. And on Friday, Xin will present us several recent work about post-pruning of neural networks with probabilistic methods. Okay, see you guys.